So last time we did, zoomed in. Last time we were covering the basic introduction to asynchronous. And we dealt with a latch. So if you remember, a latch is much like a flip-flop, except a flip-flop is extra. A latch still has memory associated with it, but essentially you have to have what our typical latch is an SR. You have to make sure both inputs are deasserted in order for it to hold. And then you either set or reset. And we said we don't want both set and reset active. Not because it's dangerous at that moment, but depending on how you release set and reset, it could be dangerous. So remember, it's not dangerous even if you assert both if you release one first, because then it'll just do the action of whichever one is still asserted. It'll still either set or reset. Now, that's kind of our base overview. So as a general rule, we say don't assert both. But let's consider some other things. Do I actually even need a latch? So let's consider for a sec a circuit. So let's consider, let's say, this circuit coming in. Put in OR, go to an exclusive OR. So let's consider this circuit. Okay? Now, does this potentially have memory? Potentially, it has. What we mean by that is, this circuit has a feedback loop. When you have a feedback loop, you have potentially memory going on here. Um, so we can look at this and say, oh, can we figure out what this circuit does, how it behaves? Now, I might, for instance, take this and say, hey, let's say I want to grab and say take this, and maybe I even have, let's do some outputs too. I'm going to grab at these two places for outputs. So I'm going to call this my input X. And let's say I'm going to say this, I'm going to call this capital Y, because I'm going to call this point back here little y. And now you might look at those and say they are electrically identical, right? Kinda. So I agree with you, they're electrically connected, but it will take a little bit of time for capital Y to go to little y. And you might be limiting very much, but at the size we're doing at the speeds we're operating on, the speed to go down that wire, depending on how thick it is and some of the material properties around it, it could be an appreciable fraction of time, which means that time delay I might want to separate what they are. And in this case, since we're building something that's so ridiculously fast, that's actually going to be a key thing. That's going to be the difference on what we need for memories. So little y is going to be the inputs coming in. Right? What the memory was in the previous time, and capital Y is kind of the output. That's the state of the memory that's going on. So they to be related, obviously, but potential time differential. It depends on the wire length and the properties of material and everything else for how fast the signal will propagate on here. Since I have an output here as well, I'm going to do the same type of a thing. Now, potentially, this could be like some long meandering wire too that I could put in here. So I'm going to use that same little convention. Capital Z is the output of the gate, and little z is the input to the next gate. That is not a very good looking little z. Okay, little z is the input to the next gate. So I'm putting those serifs on the end to try to distinguish capital, because I did handwriting mistakes. That's why I went into engineering and into art. All right, we good with basic setup of the circuit? I know I've labeled them because I am allowing some time delay. Because what we're going to kind of think of doing is I'm going to essentially, for purposes, break the wire at that point between the output and the gates. Now, I'm not going to really do it, but just analysis. I'm going to consider that a broken separated. And I'm going to make up my little table. X is my input, and then I'm going to have Y, Z. It's gonna, these are essentially all the inputs into parts of my circuit, and I'm going to consider my outputs capital Z and capital Y. Okay? All right. Now, there are some of these are pretty easy ones to understand, right? So like, for instance, little y in a short period of time will get the value of what capital Y was. And little z is going to get the value that capital Z was. Capital Z goes to little z. Now we can also say what is the equation that describes how capital Y gets it. Well, capital Y will change according to this exclusive OR gate, and it's going to be little y, little z. Fair? And how about capital Z? Any of you help me out with capital Z? What's going to define what it will become in a little instant? Yeah, I've got the little x and little y, and what happens to them? They get, yeah, a NOR gate, which is an OR and then a negation. There. So this just gives us a nice, easy way to define what's happening on these. And like I said, this is kind of our trivial one. This is the one that has some amount of state updating equation in them. So let's say I want to calculate my little table here. And there are possibilities for each x, I'm going to say 0, y and z, all right? 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. This is my possible values the inputs could take, and maybe none of them are actually end up being achieved, depending on how this is set up, but this is what could be under some case. And I know, according to these equations right here tell me how to actually calculate those y's and z's. So I can just go in for each one of these. Now I know capital Y will be the exclusive OR of little y and little z. What does that mean? Like if I want to just quickly calculate and I see exclusive OR, we should look at this an odd number of ones between the two, right? Which in this case, since there's only two of them, means they should be different if I want to get one. So I can look at y and z and say, whenever they're the same, I'm going to get a 0, and whenever they're different, I'm going to get a 1. Fair? All right. Z, I'm going to OR them and negate. So when x is a 0, 0 or y is y, so it'll be y prime. There? So under the 0 case, I just put y prime here, which is 1, 1, 0, 0. When it's a 1, 1 or y is 1 negated 0. All right? So there we go. This gives me my table from this. Now, this is kind of in truth table form, and it's nice in some sense, but it's kind of often a little bit easier to put this into more like a Cardinal map type look to the whole thing. And I can still consider that almost a table. I'm going to do something a little bit different than we've done with Cardinal maps in the past. I'm going to separate these, and along the columns, I'm going to only do true inputs, and along the rows, I'm going to do what I'm going to call incoming states. All right? And these incoming states is anywhere I've broken them. I'm saying that's a variable that I'm holding in memory. It's time memory that's traveling down the wires. I'm going to time those wires, but who cares? Right? That's up to me to have to deal with when I'm laying this out. But I'm going to do it this way. If you got an idea why I might want to split under this way, there is a really practical reason for this. How long is it going to take for capital Z to go to little c? Yeah, there's no clock, right? So it's some little time constant, and I agree. That's some short period of time depending on what it is. How about from capital Y to little yeah, it depends on how long you make wire, right? So if I give a little bit of an extra wire length between capital Z and Z, I can, by length of wire and properties, I can time them so they're pretty equal, can't I? At least close, right? So, but in both cases, are those long periods of time? No, it should be really, really short, right? These are my states. This is actually what we want, right? Asynchronous things, we want these states to be very, very fast. The only reason you would ever go to asynchronous is you need stupidly fast states, right? Regular states just aren't quick enough for you. And for whatever reason, you need them ridiculously fast. So this meets some type of requirement. So we know these, by putting the labels on the rows, I put all the fast ones there. How about the inputs? How fast are the inputs? They could be fast. How fast are they compared to the states? They're slow compared to the states. They're still fast compared to us, but usually that's a phenomenon coming in, right? And even if it's a very short transient, a delta function, how long between those delta functions coming in? Now think about most phenomena you're dealing with, right, that human beings deal with. Most of them are operating in human time, right? Whether it's wind gusts or whatever. Even if I'm dealing with something like radioactive decays or something, there's still an interval between these, and when you're comparing it to picoseconds, you're not getting multiple decays in a picosecond. And if you are, plug your nose, keep your mouth open, and hope the blast don't kill you. Right? I mean, you just shouldn't be gaining of anything. Most phenomena happening somewhere in the human state, within a few hundredths of a second, a few thousand, somewhere around there. Now, they could be transitory and hard to find, right? So in that sense, they're very short duration, so I need something quick to pick them up. But even, say for instance, like I deal with mental radiation stuff, and we do accelerators. We have a million particles hits in a second. Right? That's a million things a second. That's pretty fast to consistent. But how much time is that between each one? a little, a little bit more, and microsecond. Like millisecond is thousands, microseconds is millions, right? So you go microseconds, the next unit down is nanoseconds, and then picoseconds. We're operating in the tens to hundreds of picoseconds. How fast is a microsecond compared to that? That's 4 to 6 orders of magnitude. It's too, it's stupidly slow compared to our computer. Right? So this is what I'm just trying to get you to appreciate. These are fast phenomena, but not compared to what we just built. We have built a very, very fast memory system for the purpose of making those things look stupidly slow. Because we're trying to catch them. If we're not way faster than them, how are we going to do that? So the practical point of this is going to be the things along the columns change slowly from our computer's perspective. Human beings don't matter so much anymore, right? To the circuit we're building, those are slow signals, right? So therefore, if I get an input, I've probably got a number of time periods inside my states. So more than enough time for those states to settle out before my next phenomenon comes in. If that is not true, it is a whole nother level of difficulty. And it's going to be very hard for you to build something. So at that point, research better technology that goes faster and then okay? Because that's, otherwise you're gonna be in some deep doo-doo. When you have to do some special stuff. But that's gonna be my assumption. The inputs relative to state transitions will be slower, at least in the input between events. Even if the input is on par with it for as a spike, right, a short duration spike, the time between spikes will be slow, so I'll have time to react to it. Does that make sense? Okay. Fine. So this is just how I'm going to label it, and that way I can only think about each column when it goes in. So let me redo this slightly. So now I've got X along the top because it's slow, right? And it's a 1 or a 0. And then I'm going to slightly reorder these, right? My little y, little z, 0, 0, 0, 1, 1, 1, 1, 0, right? Why? Why switch from binary, which works perfectly fine for us so far, to gray code? Faster, so in this case, right, is how fast whatever the things transition. So in that sense, there's, I wouldn't necessarily say one is faster or slower, but there is a big advantage to gray code, right? What's the big advantage to gray code? 1 bit less. Now, we're going to think about here in a sec what goes on, but let me just do a little aside just to think about this. And imagine for a sec, I'm just going to put a single column of these, right? And let's say I start in 0, 0. And let's say that my next state is going to be 1, 1. So this is just a little fraction of your table. So I want to go from 0, 0 to 1, 1. Is it theoretically possible that I just instantly, they perfectly flip at the same time and everything goes? It's theoretically possible that's true, right? What happens though if on my gates I don't perfectly time my wires and everything else? So when I'm trying to go to 1, 1, is it possible that the one on the right transitions first? Is it possible the one on the left transitions first? Right? So now, depending on the timing of everything, which could change as it heats up and all kinds of other stuff, right? I could have any of these things happen. Do you remember what we called when different things could happen, and we're trying to see who happens first? race condition, right? Races don't only happen with inputs. So he says what we generally want to do is prevent two things from flipping at the same time. In general, it's going to be really hard to happen with your inputs, but you should try to generally make sure your inputs don't get a race condition. But realize state transitions can have races, and these are blindingly fast. So it is possible, imagine on these other ones here, what if my remaining states look like this? All right? Imagine that's my state. Because that's a possibility, right? What's my next state? If it's a 0, 0, it goes to 1, 1. If it's a 0, 1, it stays at 0, 1. If it's a 1, 1, it stays at 1, 1. If it's a 1, 0, it stays at 1, 0. Now we mark these by circling them. We call these stables. So just to make it easy to read the chart, we circle them if they're stable. Fair? Just a convention for which everybody follows. Think about my race here. The race is on. Right? If it flips to 0, 1, it's going to go here, and then what does it do? It stays there. If it magically flips to double 1, it stays there. If it flips to 1, 0, it stays there. Doesn't matter which one is first on flipping. Well, you end up in completely different states. Do you care if you're in completely different states? Yeah. So it's pretty critical that it switches correctly to how you dictate it. So we call this a critical race. Okay. The outcome of the race matters. Now, alternately, you could imagine I had a case that looked like this, 0, 0, 0, 1, a slightly different transition area. 0, 0 goes to 1, 1, right? Imagine everybody says go to 1, 1. Now, 1, 1 is stable, nobody else is. If I start at 0, 0, I could magically just go to 1, 1. At which point, it's stable and I'm done. The one on the right could change first, but if it changes first, its goal is then to go to 1, 1, which is stable. It is possible the one on the left transitions first. And if it does, right, it's going to want to go to 1, 1 where it stops. Is this one critical? It's all going to end up there. And how these blindingly yes. So is it super important, this race? So this race is not critical. So there are races that are critical, they matter. There are races that do not matter. They will not change anything. If it doesn't change anything, then it's not critical. Right? This is an important area. Are you going to worry about many critical races? No. No. You worry about critical races? Absolutely. This is where you don't want them to happen. Let me throw in one other weird possibility to you. Right? Let's imagine. I should draw my box first. Okay. Slight alteration of my little section of this, right? I still have 1, 1 is the only one that's stable, right? Now, 0, 0 wants to go to 1, 1. If it does it, yay. If it goes to 0, 1 first, 0, 1 goes to 1, 1. Does that matter? All right. If it goes to 1, 0, 1, 0 goes back to 0, 0. What happens? 0, 0. Now I've made a cycle. Because now 0, 0, it's going to try that again. But we know we're slightly sure on that second one. It'll probably repeat, At some point, it might take one of the other routes just because as it starts cycling faster and faster, it'll heat up and who knows what's going to happen to it then. Um, is this critical? Yeah. Yeah, because you don't know how long this could take an hour before it settles. It could settle in a second. Do you know? No. Could it theoretically stay in that cycle forever? Yeah, it could. So does this one matter? Just put it down. The critical, just think it matters. I don't worry about it. Non-critical means don't worry. That's all you're trying to say with those terms. Right? Does having some weird cycle like this, where some things go where they want, and randomly some things just get stuck for an indefinite period of time, does that matter to your design? Yeah. Yeah. Right? It matters. You don't want it to happen. So that tells me I have to do something to alter this because I don't want this to happen. This is bad behavior. So one of the things we're going to want to do with a lot of these is how do we recognize the problems? This is a big, big issue to us in async that we didn't worry about a lot of other things because they were already nice and safe. Because they were taught you couldn't get stupid fast races. So even if there was a slight difference between them, I waited until an edge happened. So there was more than enough time for both things to have transitioned. I never sampled it early. Now you're sampling it early, which lets these races happen. Um,
So the dad should consider that these races. These races.
Yeah, these races are potentially dangerous. This is the added thing we gotta worry about. Right? So we need to remove any race. That's gonna be the whole thing. Because remember, a race is telling you you're not sure what's gonna happen when you tell.
So we do all this.
Yes, we need to remove critical races. You know, we could remove all of them if we want to, but yeah, it won't hurt you to remove all, but you could end up with an overly big system, right? But if it's a critical race, I don't want that. That's dangerous behavior. You have to remove those. Fair enough? This gives you the added, other than this, it's just like your design you've dealt with. So we don't want really big systems. The bigger the system gets, the more states I have to jump between, the more states I have to jump between, the more likely I'm going to get races that could become critical. Right? So smaller systems are better. So we worry about things like reducing our states to get these smallest number of states. That's what we have to talk about next time. Right? How do we make sure these are small? Right? We worry about how do I make sure I only, because I don't want two things to change. Right? This is the key thing. Can I have a race if there are two people in a race? Is a race possible?
Yes.
3 people?
Yes.
4?
Yes.
18?
Yes.
1?
Yes.
Yeah. I can't race myself. Right? That's the big thing, right? I can race somebody else. I'll lose badly, but I can race somebody else. Right? But I cannot race myself. It's not meaningful. So, but we don't like races because we don't want uncertainty. Right? This is what makes things fun in real life is not fun to engineers. Right? People play sports because they're not sure what the outcome is going to be. Right? Depending on a lot of factors, things could change. We hate that. Okay? Because you don't want, hey, maybe my computer does this, maybe it doesn't. Right? It may be fun for people to gamble or whatever, or root for my team, or that kind of stuff. But it's not fun to be like, go computer, this time you can work. That's annoying. So just realize you're trying to remove unique behavior, right, from the whole system. So we're going to get critical races. Does this all make sense? So the things you're going to watch for is they end up at different endpoints. Right? If multiple things change, right, they either end up at the same point, they end up at different points, or they end up looping around. That's the three possibilities. The only one of these we like is they end up at the same point. That one you can explore. Fair? Okay. So that is my aside. Okay. So if I do this when I write as a grade, you only see one thing transition. So any movement directly on this path will be easy. You jump, that's a race. So it's just easier to kind of spot when the changes happen. If it's moving to the square adjacent to you, who cares? All right. So now I can copy them over. I'm going to write the 2 in here. All right. So we just write them in 0, 1, 1, 1. Now remember when it goes here, it drops to the bottom. 1, 0, 0, 0. And then the next one, I'm now in x equals 1, 0, 0, 1, 0, 0, 0, 0. So remember, we just have to flip the last two to go into gray order. Now we're going to do our little encirclement trick. If whatever the input was is what's inside here, we circle it and we go, hey, stable. Fine, that's holding memory. 0, 1, nope. 1, 1, nope. 1, 0. They're both stable. Fair enough? Okay. Now, looking at these, we can take a look, and let's take a look at this area and say, what do we have? Is this a stable thing? Do we have loops? What's our area going on? Now, obviously, this one is stable, so we can pretty much just ignore it. Right? It never leaves it, it just always stays there. It's kind of a sunk state. If we look at this first column, what's going on? 0, 0 goes to, 0, 1 goes to, 1, 1 goes to, right? And so what is this doing? It's a cycle, but it's a cycle with a race. Right? 1, 1 goes to 0, 0. So it's kind of like, it's almost like you've got this spot when you're starting out, assuming I started at 0, 0, right? Which I could, because I could be here and I get x goes to 0. Right? The race is on. Well, 0, 1, that's not. This is that warm-up lap. Everybody has to kind of start at the same speed. Right? And 0, 1 goes to 1, 1. Okay, we're jogging along. The second you get 1, 1, that says go to 0, 0. This is when their flag goes, and it's everybody for themselves. It could, again, do what it was supposed to do, but it's possible that it one bit flips faster than the other anytime you do those doubles. Well, if it goes to 0, 0, it just continues on. Okay? If it goes to 0, 1, what's it going to want to do? Go to 1, 1. I made a secondary little loop on here. It offed my timing a bit, but if it goes to 1, 0, what happens? All right. So I've got these kind of double loops going here. Is this critical? Not critical. This is critical, right? It's a cycle. We hate those to begin with, right? But on top of it, it's a cycle with a race in the middle. So we really hate this, right? Because it's not only a disco cycle, it's an unbelievable cycle. So this is a really bad spot where you're like, hey, I want to change stuff around. That makes sense? Okay. So we're not super happy with this. But notice, I can take any circuit, I could create feedbacks, I could break the wires. I have to have a loop to break a wire. It has to be that kind of, and the wire has to be long enough for some time propagation. But I can break it at any spots I want. Now, I could go through, this is kind of just analysis, right? I get a circuit and I say, what the heck's going on here? Now, if I didn't care about Z and I only cared about Y, that would obviously simplify the circuit a little bit. It's the fact that I wanted to see what was going on with Z, and I was using Z for something that actually caused some alterations. But let's consider for a sec, under these type of circumstances, and I want to design a circuit without a latch. That makes sense as a potential goal. What could I do under that? Well, what I would have to do is I'd have to make, in some sense, a Carnot map, and I'd have to analyze what's stable and what's not, and make sure there's no critical races going on. Because we don't want any critical races. So I could design my system off by building a Carnot map where I like the properties, much like we built truth tables before. So we could have some user inputs, and we're going to talk about how we can build these methods in a sec. Right? But as just a general, I could take whatever my user wanted, I could build a Carnot map, put the states on the names, put the inputs on their columns, and I could go in and label them. Where do I want stable states? Where do I want transitions? Things of this sort. And make sure that there are no critical races. Or if I want to be extremely careful, I could just remove all races. Also be in the thing. Right? So I could do either of those two things, right? As long as there's no dangerous stuff. I'm already now inside one of these. I'm staying with the state transitions. I could then just use KMap design and build it. That'll remove glitches. That's another thing we hate. Right? And in essence, what I would be doing, I'd have my next, I'd have my state coming in, my in states, right? I'd have my inputs along the top, and I would have whatever my output of the states are. Again, remember, output of the states is just what's coming out of the circuit. Right? And I could have this inside some big old KMap. And what that would describe is, in essence, next state logic, where I have my in states coming in, and my inputs coming in, and I have my out states coming out, and they feed back around. That feedback is going to give you your memory in essence. Right? That's what hooks the inside of that KMap to the outside of the KMap. It gives you memory. So I can totally build a circuit like this. I don't need a latch. I better time my wires well, but I can absolutely do this. Right? And because it's only wire timing between them, is it fast? Is it stupidly fast? So I achieve that thing. Now, all you did before, the only difference between this and what you did with the latches is, remember, with the latches, again, just a little aside, if I was doing with the latch, the SR latches, I had next state logic that generated S and R that went into the latch. That then gave me my out state. That then came around as my in state. And then I had my inputs. Notice it's almost the exact same thing that we did with the latch. The difference is that latch gives me a little bit, it's slightly slower, it's one of the logic on it, but it gives you some stability in this sense, right? Because you already know how the latch behaves. You know it takes care of some of that timing issue to you. But every time you get a nice feature, it slows you down. So now the question is, how fast is the thing you have to catch? Right? If what you're trying to catch is something that's faster than what a synchronous system could do, but it's not on par what an async can do, it'll be a little easier. Right? If it is blindingly stupidly fast, that push very short transition things of that sort, now you have to go to the async with all the latch. Right? So it's all about how quick you want that phenomenon to be. That makes sense? So if you can do a latch, do a latch. Is that a question for me?
No, I'm still trying to understand how you went from the YZX1 table to the loop. I can't follow that.
Oh, which, up here?
Yes.
This one?
Yeah, I can't.
Okay. All I was saying is, this is just saying, it's just mapping how states transition. So I'm just mapping out how it walked through this.
Yeah.
So imagine this was my start. I can start anywhere I want. I'm just saying, let's start. Imagine this is just one.
Okay.
So imagine we'll start at 0, 0. At 0, 0, and I had implicitly said I'm on this one here. So I'm starting here at 0, 0, and I'm saying that my input equals 0, x equals 0. And remember, x is, relatively speaking, slow compared to the states, so I'm not x to change. So I'm just saying, I just want to be able to back. If I'm in x equals 0, and I start at 0, 0, what will my next state be?
It goes to 0.
So see how the arrow goes to 0?
Yes.
Okay. When that's 0, 1, what does it do?
You go to, if you're at 0,
Okay, so I just go to 1, 1. Now at 1, 1, I go to
0,
0, 0. So two things have changed. Each of those is a bit that's being stored by something. It's some gate, it's some feedback loop, it's right. There's something that's holding that. Right? But you don't know the thing that's holding the first bit versus not holding the second bit or left and right bit, whatever makes sense. Do the two bits transition at the same speed? No. So, I have three possibilities. The one on the left is faster, the one on the right is faster, or they're magically both equal. Right? It's likely, but here's a possibility, right? Or it's close enough that you can't tell, right? There may be a little interval there. So that's the three possibilities. That's what we drew the three arrows splitting on. Because I'm saying what could happen. Right? When it's only one bit changing, there's no question. Right? If, it is just one person, it's a waste of just me. Right? You have no doubt who's going to get there and whether, there's not going to be a change, right? I'm going to make it there. So those first two ones, there's no problems because nothing else can happen other than that. The problem is when you hit that final one, 1, 1 trying to go to double 0. Right? So that you're into then different things can happen. Does the most significant bit flip? Do they flip at the same time? Does the least significant bit flip first? Who wins the race? Right?
one is 4, n is 0, and n is 1, because these are.
Because how many bits are flipping? From 0, I'm going to 0, 1. That bit is not changing. That bit is. So can anything happen other than the bit flipping? That's what really matters. When it's only one thing happening, right? If I pick two professional athletes out of the Olympics and set them up to run the fist, all of a sudden, you're not completely sure who it is, unless it's saying you somehow, 20 years later, can start every single person. Right? And by racing things, 100 meters, I always used to use Usain Bolt, even in the early 2000s. The dude was still winning. Right? I don't know if he does it, but 20 years later, he's a phenom. So, but assume it's anybody but him. Right? In 100 years, he might still be leading this race. The Blitzers are dead, but he's still beating everybody. But imagine two other people or two other professional athletes. When they race, you're not really sure who's. You have big rappers that have big little sluggers. You just don't know, right? So that's why it's a race. You're not sure what's going to happen. But whereas if you put me against a professional runner, you know what's going to happen. Well, if you just put me in a race by myself, you're going to leave me, I'm hitting on the wall. Will he make it? I'm okay. But, yeah, but I'm going to get there. So in this case, it's getting there. In this case, only the most significant is flipping. It's going to get there.
I'm saying for n
Yes,
is
but
saying for n is equal to 1. like that picture.
And you mean 1 bit? Or
No, no, so start as n equals 0.
n equals,
And then if you change that to 1.
if you change n equals 1, it's a different, but that's a different comparison. When we're really doing this thing, we're trying to think of if I'm in n equals 0, do I input x equals 0, right? Do I, because remember the input we're saying is below.
Yes,
Right? Therefore, it won't change in this time period.
but we're deciding it.
Yeah, I need to do the same exact thing for input equals 1.
Okay.
Right? I need to do this for any small in here. We should look at them and see what the transition is. Right? Technically, I would even start, to do the one here, but that's in the boring, right? If I noticed it, I could go through and just go, 0, 0 goes to 0, 1 under 0. Well, there's no race to ignore it. Right? 0, 1 goes to 1, 1. Right? No race, ignore it. 1, 1 goes to 0, 0. I could make that as my start, because I'm like, this is where it's interesting. Right? Um, we walk through all of them and look at them. In this case, we start at 0, 0 and we followed it through and we noticed, oh, A is forming a cycle and B is an annoying cycle. Right? Now, if I did the same thing and I looked at input equals 1, right? Now, yeah, I do the exact same thing, right? So, if input equals 1 now, I start at 0, 0, I'm staying at 0, 0. Boring, right? There's no change. I go to the next one, right? I start at 0, 1. I'm trying to go to 1, 0. Uh-oh, race is on, right? What happens? What I do? Up was up, right? Up was the most significant bit changes. So I'm trying to go here. I go to 1, 1, right? Because that bit changed. The other one didn't. Going down, that bit's going to change. So I go to 0, 0. Right? And then I have to ask what happens. Well, 0, 0 is stable in that column, so it stops, right? If it goes to 1, 0, that's stable, it stops. If it goes to 1, 1, it's going to try to go to 0, 0, but that is another race, right? So it could go to 1, 0, at which point it would stop, right? Or it could go to 0, 1, and I go back to the beginning and repeat this. So I've got a critical race because different outputs can happen here, right? I could either stop at 0, 0, I could stop at a 1, 0, or I could have a signal. And that's a weird thing. Right? So, again, does this one yeah, and it's that spot. I don't like that transition. So it should change that transition. Theoretically, my customer has specified some behavior they want, which usually has to do with what states you're stopping at and how you transition on an input from one of those states to something else. That's a usual big case that we're trying to deal with, right? We're being how do we move to the next thing over here. So it's usually not too hard to say, oh, this is a bad design, it'll change my circuit. But I'm going to say, for instance, let me just remove, whatever some of these double race conditions out of here, or whatever else I decide I want to do with them. All right, so maybe I don't have 0, 1 go to 1, 0, maybe I want to go to 1, 1, and whatever. I can remap them to meet some requirement. Maybe I look at this and go, wow, I've got a bunch of unused states here, maybe I should reduce my states. So I avoid these type of problems in here. All right, so there's a lot of things that could potentially be as design choices. That's what we're going to talk about at the next stage of this. Right now, I just want you to see the problems. So when I say there's a problem here, what are we going to do? Let's introduce a method. You understand why it's a problem. And you can look at it and see them. That's all I need right now. Where are the problems? And then, I better fix them. Make sense? Okay. So let's talk then. All right, so now we've got two different things. I can do latches. I don't have fab latches. Slightly faster, maybe a little bit scary. Okay, let's talk about a couple methodologies for going here. This is my least favorite one, but it has uses. So, called key and lock. Okay? And the reason I'm not as huge of a fan is this tends to make bigger stuff, and bigger stuff in my mind is always a little bit slower. However, key and lock simplifies your life. So realize its benefits, and this is relatively speaking simpler, right? But it also tends to be bigger. Here's the whole idea. Anybody ever take a look at like a quick set lock or a lot of door locks? Right? What they tend to do is you've got your key, and let's say whatever. So your key's coming in, and you've got a series of metal heights, right? Does that make sense? So, you know, boom, here's your key bit, right? Each of these heights here are designed, so inside the lock mechanism, there's a pin. And there are different length pins. And then the other half, there's another metal pin that bounce off it, and then there's like a little spring. And if your key is the right key, it lines up the interface straight along there, and that way it allows variance to turn. So you can turn the lock if it doesn't, it doesn't. There is relevances. This is why it's called key and lock. What we're going to try to do is make every condition that is specified as a requirement, I'm going to make it one of these little fully checked, tumblers inside it, right? So you can only activate my asynchronous circuit if the key is in the lock, i.e. it's activated all relevant tumblers, then it'll turn. But I remove the possibility of you messing with my state unless all the things are going. Does that make sense? It's like why it's called. If you understand the name and make the design, you'll be like, oh, okay, that makes sense, right? How do I do this? Well, what I do is every one of these tumblers, I make an enable. So maybe I have 4 different enable circuits or whatever. I have as many enable circuits as you need. So my end user could, for instance, tell me one of the requirements is, right, all the inputs has to be 1 when, this is going, or a certain subset, like, well, let's make it very, let's say like X and Y inputs have to be 1, right? X and Y inputs are 1, just to make that specific. Let's say, I then want, Y, um, and, oh, actually, let me not use Y anymore. Let me say, Z has to be 1, Z is 1 if, and I'm literally making this on the fly because it doesn't matter what it is, right? If my state, let me call my states, I'll use ABCs, right? If A is, or if I'm in A, state A, let me just call it state A. Right? I'm not going to give them numbers at this point, right? So if I'm in A, Z has to be 1, right? Or Z has to be equal to 0 if I'm in state B. B is, right? So I could then go in for each one of these. X and Y have to be 1. So to meet this is one of my enables here. So I just go, oh, that requires X, Y, an AND gate, and this is my enable 0. I go put EN 0, right? Because this is my first one. This is 0, this is 1, this is 2, right? And I need to have my enables, the appropriate enables. So I pre-calculate what those enables are, so I don't have to worry about them. And I time my enables, so they're whatever, 1 gate or whatever I specify for them. And I could go for each one of these that's going in, right? Z is 1 when A is, right? For whatever A's condition is, right? So I could check and see if I've got Z and whatever my A is, I can negate or whatever necessary to flip the bits. Right? But I could put the pattern of A as an input. You'll have multi-input AND gate, but that's okay. That gives me my enable 1. Right? And I need Z equals 0 if B is, right? So I could say B and Z prime. That gives me enable 2. Right? And at this point, I'm now doing my designs off enable, right? So I can just have these ones, and I can then just say, hey, in my tables, I don't need to worry about inputs or all kinds of other stuff. It's a very easy transition from these. I can just use these into an SR latch to set them, because I know what the enable patterns are. Right? This was a standard thing in Synchronous, right? We added those enables to, set that. It made our SR latch a little safer. Same thing's happening here. That's all key and lock is. It'll be enabled and only let the latch transition when the enables are set to the way you. And since I can have a whole bunch of them that fit together, it's kind of like those tumblers in a lock, and so that's why it's called key and lock. Right? But you can imagine with each one of these, to combine these together to get a net effect, I'm going to have to say, enable 0 and enable 1, or enable 0 and enable 2. I cut out a larger gaping and boom, here's my master enablement to meet the requirement of what they wanted. But at that point, I now have an enable, I use that enable on the latch, and boom, I'm done. Right? But realize I built kind of a big circuit with a lot of cascades to it. But isn't it simple? Yes. It's fun to do. Right? Many stages, it's not fast. No, more stages equals slower. It's a little slower, it's a little bigger, but is it blindingly safe to make sure you have implemented the correct logic? Yes. Right? If you can tolerate it, PMI is easy. So this is why I say it's not the biggest thing, because often if I'm going to go to this, I probably want speed, speed, speed. But if you can tolerate a mid-zone, I mean, heck, this is very nice as a methodology if I can tolerate that. That makes sense. Just enable it, use the enable as your transition from location. And a latch transition, we in essence turn the SR into a D. So I take whatever my net enable is. Right, so I would just take in this case EN0 and EN1. Let's just finish it. Right, this has to be enabled. That gives me my next level enable. Right, because that's my combined condition for them. So I'm going to call that 3, and I've got enable 0 or enable 2. That means all these were met and this was met. All right, that's my enable 4. And if either of these are good, I'm done. So enable 3, enable 4, stick it into an OR gate, and this is now my master enable, no subscript. Yay, enable, right? And then all I have to do is this enable. I in essence make a D latch. All you do for a D latch, input, invert, and this has become a D latch. Where this from, we made D flip-flops, this is how you make a D flip-flop. Because if the input here is a 1, S will get a 1, R will get a 0. That'll make a 1 go through. Right? If whatever's coming in is a 0, S gets a 0, it won't do anything. R gets a 1, so it'll reset, so it gets a 0. There's no way they can both be the same. I've made them the flip of each other. Right? So this is how you turn an SR into a D. So all I have to do is run my enable into my D, and boom, It'll run, it'll only do what that key tells it to do. Right? Does that make sense? So this just makes a nice, easy way to do this kind of job. Right? Anyway, you could do bigger and bigger of these things, who really cares? But the idea is just, you just think, hey, look, I got a lot of conditions to meet, it's complicated, I want to make sure they're all set, let me list them out, make little enables for each, combine the enables into something bigger, so I get a master enable, and then my state transitions only happen when enable tells it to, because that's what they told me to. And I could have a series of different locks. If I have too many states and I want different states to transition at different times, I've got a key for every state. Right? So if the key is in the lock, you can go. If the key's not in the lock, you can't transition. Easy peasy. Good? So that literally is the whole idea of key and lock. Like I said, it's big, but it's functional. All right. Primitive states. So the idea of what we're going to do with primitive states. Normally when you've done things like right now, up till now, you've put in some type of some state table that's in here. Let's just, whatever. Let's say I have different states like this, 5 states, right? And, maybe we have some transition map that, whatever, looks, we'll make these go this direction, these go up. And maybe I'll stick some 2 there, 2 there. You gotta make sure 2 go out of everything. Yeah, I think I've got 2 on everything now. So I have some state transition. Normally you'll do things like you'll go 0, 0, 0, 0, 0, 1, right? You'll just number them. However you number them, you just throw those digits in. Right? But that's not safe, because transitioning from one state to the next, you could create a. So one way I can do this is what's called primitive states. Now, I have to put transitions on this. So let's say 0, 1, 0, 1, 0. But here we go. Right? So, anybody tell me what those things on the arrows are? Those are they're the inputs, right? That's given to me. Right? I don't get to number those, because somebody just says, hey, you've got some input here, that signal is its X, and this is what it does. And according to their things, they tell me how these states have to move between them. Okay? And this is some estimate of what's going on that's doing some functionality. How do they do outputs? Anybody remember what outputs are stressed on these states? We put a slash in. Right? Now the question is, where do I put the slashes? I can put them in the states. I can put them on the transition areas. You can't do both. One or the other. That's just the rules. Okay? And the reason for those rules are it keeps it more systematic. There's some design rules to them. Anybody remember what happens if I put them in the states? What we call that? It actually has a name. These are state machines or state graphs. They're called Moore machines. If I put them on the arrows, they're called Meade machines. Okay? Because there's a slight different areas, right? And has anybody heard these? A lot of people are staring at me like I'm from another planet, right? Have we heard of these before? Here's some yes, some no's. Okay, here's the important thing about them. Right? These are just state graphs, and I have to put them somewhere. If I put them inside the states, a Moore machine, the output is only dependent upon what state you're in. Overall states means it's stored in memory. Memory is stable. So Moore machines have very stable outputs. If it's on the arrows, it's called a Mealy machine. So output, if it's in the state, then it's Moore. If it's on the arrows, then it's Mealy. And I probably should have capitalized it. It's last names of the people who did those design theories behind them, right? The outputs are always after a slash. So if, for instance, you saw here, yeah, I'll just make it 0 there. Whatever, right? You see the slash on the arrows? You can instantly tell me what type of machine is that? Merely. And it depends on the state where it came from. Right? Not the arrow where it's pointing to. Remember, the arrow is where you're jumping, right? So your output is dependent on where you are jumping from and what input told it to jump. You don't yet know your destination. I mean, in theory, the arrow is telling it to you, but you don't have the destination yet. So it can't be used to determine what the output is. So Mealy machines depend on, their output depends on both state and input. But input can have all kinds of weird fluctuations and timing. So your output copies all those weird inputs and timing. So they are not as stable. Mealy is not as stable as Moore is. So that sounds like Moore is better, right? Moore ends up making bigger. It makes more states. Because to handle all the input varieties, you need more states. That's not what it came from originally, but it's helpful to remember, right? It's abusing some dude's state. But it's at least helpful. Mealy, anybody know Mealy? I don't think it's a very common thing. Mealy's like a little annoying thing, right? Some mealy. It's an old term, right? But think of mealy as like a little teeny annoying thing, right? So mealy machines are smaller, more machines are bigger. Okay, mealy machines are somewhat annoying. They cause fluctuations on their outputs, so they're not as stable. But since they're smaller, they're faster. So you now want to use them in different cases. Right? What if you already have a stable input? You know your inputs are good.
You're not used to that, you're not used to that small thing because it's smaller and faster.
Smaller and faster.
They would put instead of output.
So if I do my first layer as Moore's and everything after it is Mealy's, I'm probably good. So this is why I wanted to see the difference, because Moores make really good buffers coming in. Or if you ever need to resynchronize timing, Moores, very, very stable, right? But they're bigger and slower and take up more of your silicon area and things of that sort. So you don't want to use them as much. Does that make sense? Mealy's stupidly fast, use them in the middle because they could be dangerous. You know, there's reasons for it. You will get to some industries, and strangely, a lot of people have never learned this. I'm guessing every class teaches it or whatever. So I have talked to people in industry who do not understand the difference, and they build things without understanding that difference. It'll run 90 some odd% of the time without any problems. Right? It's just that occasional annoying glitch that gets through. So knowing the difference prevents that rare error. But if you know what you're doing, you can make a small system that's safe, right? It's much better. So please do note it for your understanding. We feel good so far. Now, what you would normally do at this point is you would put in, like I said, you could put in like 000, whatever. But remember, that's where my base conditions are. transitioning from 0, 0, 0, and what if this is 0, 1, 1? 2 bits have to flip to go into the output. So I don't like it. I don't want to do it. So what we're going to do is we're going to introduce the idea of primitive states. We're going to letter them first. We're going to figure out everything to do from this, and then we're going to introduce whatever we want to make these things stable. But we also want to make sure, for instance, do I have extra things of what I don't need? So remember, states go along each of the rows. So I can put in A, B, C, D, and E. I've only got 2 possible inputs, either a 0 or a 1, because remember, there's only one thing before the slash, so I've only got 1 bit input. So I've got 2 columns. That's my input. I don't have a name for it because they just gave me 1 input, but it's whatever the input is. All right? And inside here, I'm going to say what it goes to. So for instance, on a 0, A goes to a B. Right? And since this is a mealy, I'm going to put the outputs after it on a slash. Now, when you go to design, you'll split them out and you'll do just the outputs in one Carnot map and things of that sort. But right now, we're just trying to summarize the state table. Help me out. Where does B go on a 0? B goes to C on a 0, and it outputs a 0. Fair? How about C? C on a 0 goes to D, and it outputs a 1, right? D on a 0 goes to B, and it outputs a 0, right? E on a 0 goes to C and outputs a 1. Fair? Okay. Now we go to ones. A on a 1 goes to D, outputting a 0, right? A on a 1 goes to D, outputs a 0. See how easy it is to write them down, turn them into a table? B on a 1 goes to E, outputting a 1. Right? C on a 1 goes to C, outputting a 1. Right? D on a 1, right, goes to D, outputting a 0. E on a 1 goes to A, outputting a 0. Fair? Okay. Now, I've only got a couple minutes left, but we can do some things looking at stability. Like, for instance, A doesn't ever stay at A. B doesn't stay at B. C does stay, right? D does stay. E does not. Right? Now, often we would have some clocks thing when we would say it's 24 o'clock. In our case, these are fast transitions. Now, could I make this graph smaller and still have the same exact effect? This is one of those, this is the basic setup of primitives, right? We can do all our analysis, we don't have to worry about the states, we'll worry about how to number them later. Right? But let me ask you, do I need all these states? Can you look at that graph and see if any of those states look unnecessary? It's kind of hard to tell, isn't it? Right? There's a lot of complexity going on and things. How can you tell if 2 things are? So we first have to come with a definition of equivalent. Okay? What we're going to say is equivalent is if we can't tell the difference, seeing what it does. Right? Now there's 2 ways you could tell if something was different. Right? You can tell if it's different if it has different outputs. That make sense? Right? So if I'm on some particular state and I'm comparing 2 different states, if they have different outputs, you may not know which one of them you're in, But you know you're getting that, right? If one state has a zero output and another has a one output, you can tell the difference. Now, but you could also tell if I'm in a particular state, even if they have the same outputs, and I give it a particular input sequence, and I go to a different location, and I can tell that location is different because it has different outputs, right? So if it goes to a different place, right, that's not equivalent, it's also different. That's going to be our two conditions, because I could give a whole bunch of input sequence, and if I could end up eventually in a spot that shows itself different, so I give the same sequence of things to you, you end up at some point giving me a different output, I can tell they weren't the same. Does that make sense? Just as a general, right? If I'm hiding someplace, right, and, you're trying to tell which one I'm in, and you see, oh, true, right? Well, he could be in any of the true rooms, right, that show up. I move to some other room, right, you now get a false, well, then you know it was a true room that led to a false room. And you know the inputs because you get to pick the inputs. Right? Input one, move to that location. You could do a whole series of these until you find a unique pattern that told me originally I started someplace different. That makes sense? If I can't, from any two routes, if I can't tell the difference, then they're the same. So what that means is, do they have a different output, and do they go to a non-equivalent route? Look at the table for a second. We can look through and we can say, well, look, right? This has a 0, 0, right? 0, 1. You can tell the difference, can't you? Right? How about the first group? 0, 0, 0, 1, 1. But you could theoretically, to distinguish between A, B, and C, you could do different inputs. You could tell which one it is, right? They're not the exact same. Right? Not A, B. It's got two zeros. Right? So could it be the equivalent of something else? It could be the same. So A, why to consider, right? The on transition, do they go equivalent? Where does A go to zero? B. Where does B go to zero? B. Where does A go to one? Where does B go to one? B. Is there any way you can tell the difference whether I started in A or B? It's impossible. They're only the same state. A and B can be reversed. They can be combined together. So it simplifies my life a little bit. Let's go on. So I can get rid of them. I can see on this chart, boom, I can remove one of these areas, right? And since A equals D, right, whatever, I can just remove D and A equals D, so I just change this to an A, right? And I find any other occurrence of D and I make it A. We redraw the chart, and you will get an indistinguishable behavior, but with less states. In general, less states means I have less problems making transitions. Okay, because I get the exact same behavior, but it's smaller, so, I can hopefully fit the smaller. We are at our time. Does this make sense so far? So we've introduced this idea of primitives. We're going to try to first step, we figure out what the graph looks like, who cares, don't worry about it, just label them. Make a table, then we start finding, we'll get a more systematic way of finding this next time. We'll talk about how we can implement bigger, more complicated systems. But then it's a smaller table to deal with, and then we can worry about how to do transitions. And there's a number of different numbering systems we can use, so we'll talk about those too. So far, so good? Awesome. Have a lovely day. As usual, you are welcome to come up and ask me questions.